Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today we're going to look at the concept of heat changes at a constant pressure and a constant volume. And this is going to be an aspect of thermodynamics which we had of course mentioned earlier and discussed in some of our previous videos. So today we're going to look at these specific changes, of course, in trying to fix one of the conditions which we had mentioned over the universe of the system. We have said that we can be able to consider pressure, volume, temperature, mass, and composition. So in this specific case, we are going to consider these two specific aspects of pressure and volumes, and try to, of course, see what is going to be the effect on the total heat of the system if these two variables are maintained. So therefore, we're going to look at this specific aspect in collaboration with the first law of thermodynamics, whereby we have mentioned that we can be able to describe the internal energy or the change in internal energy of our system using this first law of thermodynamics, whereby we have said that this basically describes the change in energy from one state, of course, to another, which we have depicted as E2 minus E1 given as such. So the second one, this of course referred to as the heat, and this was the work that was being involved in this specific change. So therefore, from this specific description of the first law of thermodynamics, we had given a different variation whereby we say that we can be able to describe this specific heat using the sum of the change in internal energy and the work given as such. So if we try to consider the mechanical work that is going to be done, especially in the concept of compression and expansion, we have said that that is going to affect the aspect of volume, and we have described the concept of work during expansion or compression as, of course, a product of pressure and change in volume that we had given as delta V given as such. So if we try to look at this, then therefore we can be able to give this particular aspect of heat in terms of work. So if I maybe give this specific as equation 1, let's consider this one as, of course, equation 2. I can be able to give this particular equation 1 in terms of course, equation 2 using this product of heat equivalent to the change in internal energy plus work. Now, work I'm going to give it as a product of pressure and change in volume given as such, and this is going to form our equation 3. So we can therefore describe this specific heat that is going to be involved in doing work, and of course the change in internal energy given as such using this specific product. So if you try to consider the concept of of course constant temperature and of course constant volume and pressure, we're going to see that the change at constant volume, this is going to depict an aspect of the delta V being equivalent to 0. And from our equation 3, if we try to fix delta V equivalent to 0, then therefore we're going to describe this particular heat in terms of delta E given as such. Now that we have said that pressure and the change in V is going to be equivalent to 0, so therefore this second aspect of the equation is going to disappear from that specific condition. So therefore we can be able to describe that specific heat energy in terms of a constant volume using this equation 4 given as such. So if we try to consider, of course, the concept at constant pressure, we can be able to derive this specific heat using this general representation for equation 3, which we have given as Q is equivalent to delta E plus P change in volume. So at constant pressure, we can be able to rewrite this equation using this specific of constant pressure given as such. And of course, we can be able to describe the change in energy, which is delta E, given, of course, as I've mentioned about this state of the change in energy from E2 to E1, given as such. And of course, the change in volume will be given as V2 minus V1, or the final volume minus the initial volume given as such. So we can be able to write this specific equation in terms of these two sets of J delta E and P delta V given in another fashion, whereby we're going to have it as QP is given as E2 minus E1 plus P V2 minus V1. So I've given this one pressure as a constant factor, and then the delta V is going to be given using that specific formula. So we can be able to do a rearrangement of this specific equation and give it in terms of the two states for the final and the initial, whereby we're going to have it given as PV2 and then minus, we're going to have E2, E1 plus PV1 given as such. So if we try to look at this second aspect of it, is going to be a negative value for E1 and PV2. So therefore, I just given them in terms of those, of course, this specific parenthesis given as such. So we can be able to check out and see that this particular aspect of E2 plus PV2 minus E1 plus PV1 given as such. Now, in our first discussion on the concept of enthalpy, I had mentioned that there is going to be some thermodynamic properties of a system that is going to be dependent only on the state of the function and not its history. And we had called that state, or rather that specific thermodynamic property, as enthalpy. And of course, this is going to be a description of E plus PV, which is going to entail this state of or thermodynamic property of a system that is going to be dependent on the state and not the history of a system. And we had given an initial to represent this enthalpy using H. So H is a product of internal energy plus PV given as such, and therefore we can be able to describe this specific aspect of course, enthalpy using this specific aspect of the derivation of heat at constant pressure given as such. So therefore, in this specific case, we're going to portray this aspect of enthalpy, which is going to be considered as the heat content of a system that can be described using this specific aspect of a constant pressure, which I've given as such. So in our next discussion, we're going to look at various aspects of the changes in volume, temperature, and pressure. Of course, and try to see how this specific system is going to behave in trying to vary those specific aspects that I've mentioned in this particular case. So I hope that this is going to give us a clue on the heat changes, how we can be able to describe the heat changes in terms of the constant pressure and volume, which are given in these two specific states, whereby I've said that if the delta V, which is the change in volume, is going to be 0, then therefore we can be able to describe the heat change, which is going to be given as the difference in internal energy, which we had of course mentioned as an aspect of E2 minus E1 given as such. And then we have said that if the pressure is going to be kept constant, then therefore we can be able to describe that heat of a system using this specific aspect, which is going to assist us derive an aspect of enthalpy that I've mentioned in this particular case. And I've said, of course, that the enthalpy in this case is going to be conceived as the heat change or the heat content of that specific system. So check our description boxes for various other videos which are going to be related to this. And of course, I'm going to put a link of the video of thermochemistry or thermodynamics in our description box so that it can assist us understand or have a comprehensive overview of these specific topics which are related in one way or another. So that is it for now, guys. Bye. God bless you. Catch us in our next video.